Hi guys, in this video what we're going to do is look at what's called differentiation by rule. In the last video what we looked at was differentiation from first principles, and it's quite annoying and quite time consuming to do every single function from that. So what's happened is mathematicians have come up with a bunch of rules depending on what type of function happens to be differentiated. So for example here we see we have f of x here is equal to x to the power of something. Then this is the derivative. Cos x becomes equal to minus sine x differentiates to cos x, and tan x differentiates to sec squared x. Now sec x, if you can't remember what that is, so sec x is equal to 1 over cos x. So sec squared x is equal to 1 over cos squared x. Now, as always in maths, there's numerous ways of writing the same thing. So you can see here that what we have in the tables book, f of x, the derivative is given by f dash x. You've seen in the previous videos that I've done that if y is equal to a function, then we can use the dy dx is equal to the derivative. And if we wanted to, what we could do, instead of putting dy dx here, you can see that y here is equal to x to the n. We could replace the y with the function. So dy becomes dx to the n over dx is equal to whatever the rule happens to be, which is this one here. Okay, so let's see how we use these. So a couple of examples here. It says differentiate with respect to x to the power of 4, 1 over x cubed, and 1 over root x. Okay, so the rule we're going to be using here, this is the power. So x to the power of 4. So y is equal to x to the power of 4. That means dy dx is equal to, well, what it says is to bring down the power. So look, n comes in front of the x. So bring down the power and take 1 off the power. So if we bring down the power, we're going to get 4 in front of the x. So that becomes equal to 4. Rewrite the x and take 1 off the power, 4x cubed. And we're done, lads. Simple as that. So if you just have a bog standard x to the power of something, bring down the power, rewrite the x, take 1 off the power, and that's pretty much explained in words. Okay, let's have a look at the second type. The second type looks as if it's going to be a little bit more complicated. We have y is equal to 1 over x cubed. And what we need to do here is we need to get it of the form of nx to the power of something. Okay, so we need x to the power of something. We were going to try and transform it so we get to this form here. Okay, so x to the power of n. Now what we can do here is we can use our index laws, and the index law that I'm going to use is if I have 1 over x to the n, that's exactly the same as x to the minus n. We've done that in indices. Okay, that's going to use that for part 2 here. So you can see here we have y is equal to 1 over x cubed, which means I can rewrite this as y is equal to x to the minus 3 using the rule I've just stated there. And that now means I have it of the form of x to the power of n, where in this case my n is equal to negative 3. Notice I have not differentiated yet, so therefore it's still y is equal to x to the minus 3. Please do not change the notation until you've actually differentiated. I am now going to differentiate, so I now have dy dx is equal to, bring down the power, minus 3, rewrite the x, and take 1 off the power. Now minus 3 take away 1 is minus 4. Now don't add 1 to the power. A lot of people make that mistake. Okay, and if I want, I can rewrite it of a different form. I can say that's the same as minus 3 over x to the 4 if I want to take the power back underneath. Generally when we differentiate, what we do is we just leave it of this form because it's generally easier to differentiate again. Most of the time, or some of the time, we want to differentiate it twice. Okay, let's have a look at number 3 here, or part I. We have a couple of issues here. We've got it on the bottom again, so we've got 1 over root x, and y is equal to 1 over root x. Well, we know that root x, again, it's another index law. You're really going to have to be on top of your index laws in this section. We use it a lot in differentiation, and we should know that root x is equal to x to the power of a half when it comes on one of my index laws. So you can see it's on the bottom. So instead of being x to the half, it's going to be y is equal to x to the minus a half. So notice again, what we've done is we've used our laws of indices to get it of a form that we can differentiate, which is this top one here. Okay, I'm now going to differentiate it. So dy dx is equal to, bring down the power, minus a half. Rewrite the x, take 1 off the power, minus a half, minus 1 is minus 3 over 2. And you can leave it of that form, or if you want to tidy it up a little bit, you can say this is exactly the same as minus, and it's 1 over 2x and to the 3 over 2. Okay, so let's have a look at a few more examples. Here you can see that we have 7x to the power of 4 minus 9x and 12, and you can see here that we have some coefficients in front of the x's. Now all we do is we just essentially ignore them and just complete the rule that we did before. So if we have a look at y is equal to 7x to the power of 4, we can see again it's this rule here. We have x to the power of something, so we're going to use the same rule we used on the previous slides. The 7 just remains there, so dy dx in this case is equal to, leave the 7, bring down the 4, so 7 multiplied by 4, rewrite the x and take 1 off the power, 4 take away 1 is 3, and then tidy it up afterwards. 7 times 4 is 28 x cubed. Go through that again. So you bring down the power, 4, rewrite the x, take 1 off the power, and the 7 was already in front of it, so 7 times 4, which is 28 x cubed. Okay, let's have a look at the second one. So we have y is equal to minus 9x. Okay, the same sort of idea. What we have here, this here is x to the power of 1, so we can stick that in if we want. So if we bring down the power, so rewrite the 9 first of all, bring down the power, so dy dx is equal to minus 9 multiplied by 1, rewrite the x, take 1 off the power, we get x to the 0, which now means that we have minus 9 times 1 times x to the 0. Any number to the power of 0 is just 1, so we end up with minus 9. So dy dx is equal to minus 9. The simple rule, guys, is that if you see anything x, so minus 9x, all you do is you just leave the x off it and you're just left with minus 9. Another example, if we had y was equal to 12x, then get rid of the x and your dy dx is equal to 12. If you think about it, if I just go back to this y is equal to 9x, if you think of a straight line, that's a straight line with a slope of minus 9, and dy dx, the differential, is just working out the slope of that line at any particular point. It's always the same, it's a straight line, it's minus 9. Let's have a look at the last one, I, and that there is y is equal to 12, and what's dy dx going to be equal to? Well, in order to look at this, let's just graph this one very, very quickly. There's my x, there's my y, and the graph of y is equal to 12 looks something like that. So that's y is equal to 12, and hopefully you can see it's a straight horizontal line, which means that the slope of this line, you can see it doesn't change, and it doesn't go up and it doesn't go down, so the slope is equal to 0. So dy dx of that is equal to 0, and it's a constant. Notice that 12 is a constant. It doesn't matter what a constant that you get given. So if it's a constant, then the differential of a constant, because it's a horizontal line, will always be equal to 0. Okay, so look at a few more. So these lot are pretty much the same, apart from what we now have is we have two terms that we're going to have to differentiate. And if we add or subtract a term from another term, then that's quite all right. All we do is we differentiate term by term. So here we've got the first term, the second term, this is taken away from this term, this one's added to this term. As long as it's taken away or subtracted or added to another term, we just differentiate term by term. So first of all, let's have a look at the first one. So we have y is equal to 2x squared minus 1 over x. Now remember, we want to get this in terms of an index or its index notation. So we've already done this in one of the previous slides, I think. So we can change it and say that y is equal to 2x squared minus x to the minus 1. Remember, if you're not sure, 1 over x is equal to x to the minus 1. That's from our index laws. So now we have it of the correct form that we want. Everything's in index form, which again, we're just using this rule here. So you can see we're going to do this first one, just circle it in blue, and then we're going to do the second one. I'll just circle that one. We're going to do them separately. So hopefully you're spotting the pattern here with these things. So this 2 is going to come down. So 2 by 2 is going to give us 4, and then we're going to take 1 off the power, so it's going to be 4x. So the first one's dead straightforward, 4x. This is dy dx is equal to 4x. And again, what we're going to do is going to bring down the power here. Minus 1 times the minus is going to give us a positive. So we're going to get plus, and we're going to get x, and then we've got to take 1 off the power. Remember, minus 1 take away 1 is minus 2. Okay, so that's what we're going to end up with. Then tidy it up, we get 4x plus 1 over x squared. So all I've done at the end here is undo the index and change it back to its fractional notation. Let's have a look at the second one. Go back to black. So we have y is equal to 3 cos of x plus 2 tan of x. Okay, so what we have here is 3 cos x is the first term, plus 2 tan x is the second term. Cos x, again, go up, have a look. You can see cos x is equal to minus sin x, and it's multiplied by 3, so it's just 3 by minus sin x. Okay, and then we've got plus, and then we have 2 by tan x, and tan x is given by sec squared x. I'll talk about that in a second. So plus 2, and we have sec squared x, and just tidy it up, so we get minus 3 sine x plus 2 sec squared x. Now, if you're not sure what sec is, I'll just quickly talk about it. It comes all the way from trigonometry, and in trigonometry there are 3 fractions that we use all the time, because mathematicians couldn't be bothered writing 1 over cos of x, 1 over sine of x, and 1 over tan of x all the time. They just gave them new names. So 1 over cos x is called sec x, 1 over sine x is equal to cosec x, and 1 over tan x is called cot x. So if you see sec, cosec, or cot, then you know it's 1 over cos, 1 over sine, or 1 over tan, depending on which one you see. So this one here, 2 sec squared x, is 1 over cos x all squared. Okay, it's 1 over cos squared x, essentially. Okay, here's a little bit of information. It says once the derivative has been found, we can evaluate it essentially anywhere on the slope. So if we are given a function, f of x is x cubed plus 2x squared minus 5x plus 1, we're asked to find the derivative, f dash of x. That's just essentially what we've just been doing. The instantaneous rate of change of f when x is equal to 3, and then find the slope of the tangent to the curve at the point where x is equal to minus 1. These 2 questions are asking us to do exactly the same thing. Remember, the differential works out the instantaneous rate of change at a particular point, but it also works out the slope of a tangent at a particular point. These 2 things are exactly the same technique. So first of all, let's have a look. We're going to find the derivative of this. So f of x is equal to x cubed plus 2x squared minus 5x plus 1. I'm trying to work out f dash x. Remember, f dash x is also the derivative, and that's equal to, go through term by term, and we have this going to come down. It's going to be, bring down the power, rewrite the x, take 1 off the power, so that's 3x squared. We did the 2x squared in the last slide, so bring down the power. 2 times 2 is 4x to the 1, so that's just 4x. Remember, we stated that if there's any number in front of an x, then all we do is we just keep the number, so that's minus 5. And the last one there, the plus 1, this is a constant, so therefore it disappears. So the derivative, or f dash x of f of x here, is 3x squared plus 4x minus 5. So the next part of the question asks us to find the instantaneous rate of change when x is equal to 3. So what we're going to do is we're just going to put f dash of 3. So essentially what I'm saying here is I'm going to put 3 through my derivative function. Okay, and I'm just going to put it straight through. So it's equal to 3 by 3 squared plus 4 by 3 minus 5. So 3 squared is 9, 9 3s are 27, plus 12 minus 5, and that's 27, 39, 34. So the rate of change, the instantaneous rate of change when at the point when x is equal to 3 is 34. So that's also the slope of the tangent. I, last one. So what we have here, it says x is equal to minus 1, so we're going to do exactly the same thing. So f dash of minus 1. Put minus 1 in this time, we get 3 by minus 1 squared plus 4 by minus 1 minus 5, and that's equal to minus 1 squared is just 1, so that's 3, minus 4 minus 5, and that's equal to minus 1 minus 5, which is minus 6. Now there's also another way that you might see this. So if I use the y and y and dy dx sort of notation, I get y is equal to, in this case, x cubed plus 2x squared minus 5x plus 1. My obviously dy dx would come out to be 3x squared plus 4x minus 5 as before. But if I'm using this notation, if I want to evaluate an instantaneous rate of change or a slope to a tangent at a particular point, this is the notation I use. So x is equal to 3, and then what I do is I would put the 3 through. So it's 3 by 3 squared plus 4 by 3 minus 5, and then I'd carry on and finish it off as I did previously.